Dima, this is a colloquium, so I should.
Yes.
I did put in introductory material. I know there's experts.
Correct. Of course. So you should not even assume that these are condensed matter people. So of course these are non-experts.
Yeah. Okay. Yeah. So try not to offend the experts, but also provide something that students and postdocs.
Yes, the expectation is that our senior undergraduates should be able to understand it. So you really need to have a lot of introductory material. Otherwise, it's better to miss. I think for a colloquium, it's always better to make a mistake on the size of additional explanations.
Yeah. Okay. Well, we'll see how I do. Whether I strike the right balance, that's always the colloquium it's trickier than obviously.
Yes.
It's harder than giving a condensed matter seminar.
No, of course, but with your topic, it's basically a topic. It's essentially a textbook topic. So in that sense, it's perhaps should be somewhat easier. Okay, so I see that's 4:03, and I don't want to delay this too much because I will spend some time introducing you, and then we have to start the colloquium. So maybe I'll just start an introduction, and then we can start the talk. So it's a great pleasure for me to introduce our today's speaker, Professor Mike Manfra. Professor Manfra got his undergraduate degree from Harvard, and subsequently he got his PhD degree from Boston University in 1999. And after that, he spent 10 years as a member of the technical staff at Bell Labs. In 2009, he moved to Purdue, where he remained ever since. Now, Professor Manfra is a fellow of the American Physical Society, and in Purdue, he does a job of 4 different people. His official title is Bill and D. O'Brien Distinguished Professor of Physics and Astronomy. That's the first title. Second, Professor of Electrical and Computer Engineering. Then a Professor of Materials Engineering. And finally, Scientific Director of Microsoft Quantum Lab Purdue. So as you can imagine, he is exceptionally productive, and I could never understand how people can possibly be so productive. But unquestionably, Professor Manfra has been a leader in the field of mesoscale and nanoscale electronics for a long time, and this, of course, includes the field of quantum Hall effect, which will be the subject of our talk today. Now we actually initially planned to have this talk more than a year ago, but for various reasons, including obviously the pandemics, it was delayed. And normally that's a very unfortunate circumstance. But here we have also a positive side, because during this long delay, Mike Manfra's group performed an exceptionally important experiment. And the talk will tell us about this very major discovery, the direct observation of anionic statistics. This was performed in the simplest quantum Hall state, what we call the filling factor of unsought, that was discovered as long ago as in 1982. And very shortly after the discovery, leading theories began speculating that the particles that are present in such systems are not bosons, they are not fermions, but they are something else, anions. And yet, any direct observation of that remained elusive for 4 decades. And finally, this is achieved, which means that all quantum textbooks have to be rewritten. They always tell us that all particles in the world are either bosons or fermions, and now they lost the excuse for telling that. Now everyone has to admit that there is an infinite number of types of possible statistics in quantum mechanics, because today we'll see with our own eyes how this happens, and we'll get a first-hand account of a very important recent experiment. So let us welcome Professor Manfra at Brown. I know he will not be able to hear how we clap our hands, but nevertheless, let's follow our tradition. So welcome to Brown.
Thank you very much, Dima, for that kind introduction. And Yeah, I hope to tell you in a fairly straightforward way about our recent observations or direct observations of anionic braiding statistics in the fractional Coulomb Hall regime. And I want to mention this is something we've been working on for the last several years, and really a great deal of the credit needs to go to an extraordinary researcher who is now a postdoc in my laboratory, James Nakamura, and he's just been exceptional and is really doing a great job. Equally talented people are also in my growth facility as well. We actually grow the samples that we fabricate into devices and then measure. And so these samples, which are sort of a relatively new type of sample, were grown by Xuan Liang and Jeff Gardner. So these three people are the ones who really deserve all the credit. Okay, let me move on here. So this is a colloquium, and I'll do my best to give an introductory explanation to the basics of quantum Hall physics and also what I even mean by the concept of an anion. So I'm going to tell you about anions and the fractional Coulomb Hall effect. I'm going to tell you about the Aronoff-Bohm effect, which you may or may not have heard in the past, and how this can be used to measure braiding statistics in electronic Fabry-Perot interferometers. And then I'll tell you about the challenges of operation of electronic Fabry-Perot interferometers in the Coulomb Hall regime, and how in order to get at the statistics of these excitations, we had to come up with a new heterostructure design and device design. We'll first talk about the operation of the interferometer in the integer Coulomb Hall regime. That's sort of where we think we understand things fairly well, and we don't get too concerned about fractional charge or fractional statistics, to give you a point of reference. And then we'll extend that to the fractional Coulomb Hall regime, where things get more interesting. And finally, I'll try to tell you exactly what's in our data that allows us to conclude that we are making an observation of anionic braiding statistics. Okay, so for everyone who's not in the field or not condensed matter person, 2020 was a pretty big year. I think anions were sort of convincingly demonstrated in experiments, and I'll point out two. There was a demonstration of fractional statistics in what's called an anion collider, and this was done by a group in Paris. And this is the experiment, or just the title I show on the left, and below the title you see an illustration of their device. And I can't go, this is a very elegant experiment, very beautiful. It has to do with, but it's pretty sophisticated and a little bit tricky to understand. But basically what they're doing is inferring the anionic statistics by looking at correlations in shot noise, in current correlations, basically, when two anions come into what's called an interaction region, and their partitions off, and the noise signal associated with this partitioning is measured, and the correlations between the measurements at one side and the other are then used to extract the statistics. And it's, as I said, a beautiful experiment, and it is with theoretical expectations beautifully, and so it's a really great advance. It is a little hard to see direct. You're not seeing it directly. You're inferring it from what as I said, the noise correlations look like, but it's simply great. Now, we took a different approach, and where I think you can see more directly the influence of phase and the anionic phase. And if you're worried about phase and the accumulation of phase as one particle goes around another, an obvious thing to pursue is an interference experiment, which should directly be able to access the phase that's developed in this type of experiment. And that was our experiment, and I think these experiments, both the French experiment and ours, complement each other very well, and together really provide some strong evidence that in the fractional Coulomb Hall regime, at least, we are dealing with excitations that have this very unusual behavior of having both fractional charge and fractional statistics. Okay, so what is an anion, and what do I even mean by this? And here we basically have to get into what quantum statistics means or implies, and the differences that you may have depending on the dimensionality of your system and how 2D versus 3D actually can lead to different results. And so what do I mean by quantum statistics? I'm asking the question, what happens to a many particle wave function under exchange of identical particles? Or another way of saying it is, for our purposes is equivalent, but is braiding identical particles. If I take one and loop it around another, what happens to the system under that process? And in 3 dimensions in our basic quantum mechanics class, we of course learned that we have 2 types of particles, 2 types of statistics, bosonic and fermionic. Okay, bosons are if you exchange 2 particles, the many particle wave function comes back onto itself. You get the same wave function back under exchange. If you want to think of it in terms of phase, you pick up a phase factor of 2 pi. And there are fermions, and what happens under exchange, as everyone knows, on exchange of identical particles for fermions, is that the wave function gets multiplied by -1. You get the same wave function back, but in terms of phase, you can think of it as acquiring a phase factor of pi. And in 3 dimensions, under certain assumptions of single valuedness of the wave function and how deformations can be made in 3 dimensions, these are the allowed symmetries, bosonic or fermionic, and that's it. That's what we all learned in our basic classes. In 2 dimensions, though, in reduced dimensions, things can be more complicated and potentially interesting. You can have fractional statistics, what are called abelian anions. That's what I'm going to talk about today, where the phase factor that is picked up is not necessarily 2 pi or pi, but can be a rational multiple of 2 pi. And so you can imagine the wave function being multiplied by e to the 2 pi alpha, where alpha is what we call the statistical or abelian phase factor. And a prominent example of this occurs in the, or is predicted to occur in the fractional Coulomb Hall regime. And there's also the possibility for non-abelian statistics as well, and even more strongly interacting and exotic systems, say the nu equals 5 halves fractional Coulomb Hall effect and topological superconductors. And here, when we exchange particles or undergo a braiding operation, what it actually corresponds to in the case of non-abelian states is that we don't just pick up a phase factor, we actually undergo a transformation within a degenerate manifold. So it's a unitary rotation within a degenerate manifold of states. And the reason why these symmetries are allowed or not allowed comes down to basically what happens to the wave function if you take the particles around each other multiple times. And in 3 dimensions, you can imagine exchanging particles twice. And so you come back to the same configuration you started with. And in that case, the only allowed symmetries are those of bosons and fermions, because basically that can be deformed and as a identity operator. You come back to the same state in 3 dimensions, it's like doing nothing. So you can either pick up a sign of 1 or -1, and that's basically it. But in 2 dimensions, it's a little bit more complicated because braiding particles around each other in a specific way has a well-defined meaning. And you can't deform it to the identity operator necessarily. Of course, bosons and fermions can exist in 2D, but for certain classes of systems, you cannot deform those into the identity those types of operations into the identity operator. And that's where you get the possibility, at least theoretically, to have these more exotic types of statistics. And so it comes down to the end, because the world lines can form knots in 2D, while in 3D, exchanges can always be deformed into identity operators. And that's the key difference. You can't basically cut through in 2D to bring the particle back to its original state without crossing the other particle, if you want to think of it in sort of very simple geometric terms. And this was recognized, as Dima alluded to, quite some time ago, theoretically, in the late 70s and early 80s. And I think, I'm not the expert here, but Frank Wilczek coined the term anion for just a quip for saying, you know, anything's possible, anything goes in these systems. So I think that's the genesis of the name. But as you have already heard, these ideas are not new, but the experimental realization or confirmation of them has taken some time, and that's part of the story I hope to tell you now. Okay, so what I told you we have to sort of work in 2 dimensions in order to have a chance of looking at these types of things. So what 2-dimensional system will I be describing today? And that's the 2-dimensional electron system that resides in fairly simple semiconductor heterostructures, where I take basically make a layer cake of a narrow band gap material, say gallium arsenide, and on top of it, I grow another semiconductor with a larger band gap. In this case, it's the alloy aluminum gallium arsenide. And then I provide a source of electrons. That's the silicon doping that we can do in these systems. And I grow this by an advanced technique called molecular beam epitaxy. And the advantage of molecular beam epitaxy is that I can do this in a very controlled fashion, sort of with monolayer precision. I can control the alloy composition of these materials with a great deal of accuracy. I can put the dopants in exactly where I want. And sort of by design, I can make up this layer cake to suit my needs. And this is a very simple structure. The cartoon layer stack I show you in the middle is representative. It's just a layer of gallium arsenide that has a stack of aluminum gallium arsenide, which has a larger band gap on top. And if you look in the right-hand panel, you can see this is a simulation of the gamma band, basically the conduction band profile as a function of depth into the stack. And if you want to think of this very simply, the red line or curve represents the potential energy of it's a conduction band edge, but in terms of how the electrons look at it, it's just the potential energy as a function of position, and it's not constant, obviously, as a function of depth into the semiconductor stack. And there's a little potential well at about 100 nanometers if you look down along this this graph, and that's where the electrons will pile up, and they get stuck there at low temperatures. And effectively, they become 2-dimensional in that they cannot move in the z direction, but they can move freely in the xy plane. So perpendicular to this interface where you see the dramatic change in the potential energy at 100 nanometers, they get stuck there. But because of the control we have in the MB growth process, they're really free to move in the XY plane, meaning that the disorder is very low, and so they have a great deal of mobility, if you will. They can move around, and they're not just scattering off all sorts of defects. So this is interesting. On the left-hand panel, another cartoon where we have the little blue spheres that represent the electrons. They're confined to this 2-dimensional plane. But very interesting things happen when I apply a perpendicular magnetic field represented by these arrows and vectors. And the combination of the applied magnetic field, the reduced dimensionality of the system, and its cleanliness all work in concert to give rise to a variety of very interesting effects. And that's what I'll tell you about first. Okay, so again, this is a colloquium, and I know there are, of course, world experts in this topic in the audience, but there's also students and postdocs and people who aren't experts. So I'll try to give, without boring the experts, introductory lesson in quantum Hall physics. And so if we take this 2-dimensional plane of electrons and apply a perpendicular magnetic field, represented here by the cross product of the gradient operator and the vector potential, we can write down what the Hamiltonian for the system may look like. And the first term is just the kinetic energy term for free electrons in 2D and in a magnetic field. And as you learn in your intro quantum mechanics class, the momentum operator is replaced by the momentum operator minus the vector potential. That quantity is squared over 2m, and that's the simple kinetic energy term. Now, of course, this is a real system, meaning we make it in the lab, so there's always some disorder in the system. We try our best to make it clean, but there's always impurities or defects, and this gives rise to a disorder potential as well. Importantly, there's also the mutual interactions of the electrons themselves in this confined in this plane. And so these mutual electron interactions turn out to be the source of a great deal of interesting physics. They're necessary to explain the fractional quantum Hall effect. Now, interestingly, you can more or less ignore them for the most part in describing the integer quantum Hall effect. And that's what I'm going to describe to you right now to just give you a simple introduction to how quantum Hall physics might work. And then I'm going to just tell you that you can extend this to the case where we have strong interactions, and it gives rise to very similar phenomenology while having a very different origin. And that will give rise to these fractional charges, excitations with fractional charges, and fractional statistics. So let's just consider non-interacting electrons in 2D and in the presence of a large magnetic field. And this is a Hamiltonian you can actually solve. We learned this in our basic quantum mechanics class. And even semi-classically, we have a good intuition for what's happening. We turn on this magnetic field, and these electrons in the plane undergo semi-classically cyclotron orbits, these little orbits that go around in circles. And as you can see, the cyclotron frequency is given by E, the product of E, B over MC. So E is electron charge, C is the speed of light, and M represents the effective mass of the carriers. But what's important here is that this cyclotron frequency scales with B linearly. So as we increase the magnetic field, we increase the cyclotron frequency. Now, I'm not going to go into the gory details, but again, you can solve this problem of this very simple Hamiltonian exactly. And you can write down the eigenstates. The eigenstates form, of course, depends on the particular gauge you choose, but that's not really relevant here. The point is you can write down the wave functions explicitly, and they depend on two quantum numbers, what I call N and K here. N is, you might consider the principal quantum number, and it has to do with the orbital quantization. It's called the Landau level index as well. But again, and the K represents or is related to the crystal momentum in the momentum rather in the associated with these wave functions. Now, but there's two quantum numbers associated with the eigenstates. Now, the eigenenergies turn out to be relatively simple. It's just h bar, Planck's constant, times this cyclotron frequency that I've shown you above, times n plus 1/2, where n again is the same principal quantum number, or what's called the Landau level index. And so, this is called the Landau level, or associated with orbital quantization, and it was Lev Landau who first solved this problem, I think, in the early 1930s, so shortly after the development of quantum mechanics. But what the key point for us in our discussion here is that the eigenenergies only depend on n, this Landau level index or principal quantum number, while the eigenstates are specified by two quantum numbers. And so that implies that there's a degeneracy in the system. And this is what we call positional degeneracy. It's given by the area covered by the 2D electron gas times the magnetic field divided by phi naught, where phi naught is just h over E, the magnetic flux quantum. So as you can see, as I scale B, as that goes up, the positional degeneracy increases linearly with this application of magnetic field, and that has very important consequences. So let's first look at the panel on the right, where I just, I wish I could point to it, but gives you a schematic of the density of states. So as you imagine, as I turn up this magnetic field, my density of states becomes more and more singular, in the sense that, as I said, the energy levels are separated by h bar omega c. That's the spacing between these kinetic energy levels, and that spacing becomes larger and larger as I crank up the magnetic field. But also the degeneracy of the levels increases as we crank up the magnetic field. So you get this very discrete spectrum, and you can imagine that will have important consequences for the transport properties that we'll discuss shortly, electronic transport properties. Now, to keep track of what's going on in systems like this, where we have a density of electrons and we have a degeneracy of the levels, we define a quantity called nu, which is called the Landau level index, or the filling fraction. And nu is defined as the ratio of the density of electrons times the magnetic flux quantum divided by B. Okay, so it's basically how many orbitals do I have available to me compared to the number of electrons that are in my system. And as you can imagine, as I crank up this magnetic field, I can accommodate lots of electrons on these individual Landau levels. So you can imagine here where I could have a situation where the density of electrons and magnetic field, or the ratio of those quantities, are such that I completely fill one Landau level. All my electrons sit on one Landau level. Now that's the lowest one that I've colored blue here. Then the chemical potential would sit in the gap between the lowest Landau level and the next lowest lying Landau level. And you could expect that this would have dramatic impact on the transport properties, where I have my chemical potential in a gap that's well separated. I have this high degeneracy, and that will impact what I see in transport. Now, of course, this can be continuously tuned. I could have any value of nu that I want, and it could be that I have 2 Landau levels still. Now I have twice as many electrons as I have states available to me in any one Landau level, so I have to fill 2 up. And then my chemical potential would be between the second Landau level that is full and the third one that is completely empty. And again, this is where we will see the phenomenology of the integer quantum Hall effect. Now, of course, there's nothing that says the chemical potential has to be in the gap. It could be that I have 1 Landau level that is not completely filled. All my electrons can be accommodated in that Landau level. My chemical potential should reside right there in this level. It costs no extra energy to add an electron to that Landau level. You know, there's no gap to overcome. And then you would expect the transport properties to be quite different. And this is what we will see. And this is basically the origin of the integer quantum Hall effect. And I'll just keep plowing ahead. So imagine we have, and again, this is tuned by application of magnetic field or tuning the density of electrons, but we're in a situation where we have a fully filled Landau level. It could be an integral number of them, 1, 2, 3, doesn't really matter. This gives rise to what we know as the integer quantum Hall effect. And here's a little cartoon picture, again, semi-classically, of what's going on. All those circular orbits that are colored black and are in the interior of the sample are completely full. And they're occupied by electrons. There's no states available nearby that are empty, and there's a gap to any excitations. And so the states in the bulk actually carry no net current in this configuration. The bulk is an insulator. And so even though we're going to see transport through this kind of device, the bulk is essentially gapped out. Now, the little semicircles that are along the periphery of the sample and are colored red, you see that there's a directionality to these what we're going to call skipping orbits in the semi-classical description, that they are those states at the edge actually do reside at the Fermi energy, because there's a change in the potential as you reach the edge of the sample, and they are allowed to carry current. They're at the Fermi level. But as you can see, they all have a directionality to them. So they're all going in one direction. And in order to backscatter, they'd have to go through this complete insulating state in the middle and join up with the states on the far side, on the top, if you will, of this particular cartoon, and to generate scattering. And so the upshot of this is if we hooked up leads to the sample, all the current is carried by something we call chiral edge states. I'm not going to get into the details of that. It's not critical, but you get the physical intuition by just looking at this picture. And the velocity of these states, again, is something you can derive essentially classically, and it depends on the confining potential at the edge and the magnetic field that's applied. So what happens if I start driving a current through the system and trying to measure the longitudinal resistance or voltage drop and the transverse voltage drop? Well, as I said, the current can only propagate along the edge. And so, and again, since they can't, the states on the lower edge can't couple the states on the top without going through this bulk insulating region, you actually see that they don't backscatter. There's no state to backscatter into. And so if you measure the voltage drop, or equivalently just the resistance along the edge, you see zero backscattering. So the resistance along the edge in the integer regime is 0. Now, concurrently, if I measure the transverse voltage, or the two-terminal resistance or conductance, really, but that's what we call the Hall voltage, the voltage drop across the sample that's perpendicular to the direction of current flow, you find that each filled Landau level contributes 1 quantum of conductance. If we measure the conductance, it's actually in these particular states where we are at exact filling, given by nu times E² over h. that implies that if I measure the transverse resistance, it'll have units of 1 over nu h over e squared. And so as long as I'm sitting in one of these integer states, the Hall voltage or Hall conductance is quantized and fixed. And so that gives rise to what I'll show you very soon, the what we call the quantum Hall plateau. And it's just basically the number of these edge modes. It's governed by the number of edge modes we have propagating along the periphery of the sample. Okay, so that's a cartoon. I've been talking about this for a while. Now, in this description I've just given you, it's completely single particle. I've just talked about it, single particle levels, and eventually I'm going to talk about the fractional Coulomb Hall effect that would seem not to be consistent with this scenario. And that's really because I've only considered the kinetic energy term so far. So imagine we go to a filling factor that's below 1, where I have many more states available to me than I have number of electrons. And there's very specific values that are quite interesting. So say I go to filling factor 1/3. In my simple single particle density of states picture, you see below, the Fermi level should be just smack dab in in this lowest Landau level. Nothing much interesting should really happen in this picture I've given you so far, because there's no gap to excitations. There's nothing special about it. I could add another electron, it seems, with impunity, not with any significant energy cost. So you would expect that there's this huge degeneracy. The expectation is that this state is very compressible, meaning what I mean by compressible is that my chemical potential is not in a gap in this particular case. But it turns out this is because of my neglect of the electron-electron interactions. And so the electron-electron interactions are really what's going to give rise to all the interesting physics that we'll discuss shortly. And if you think about it, this actually it kind of makes sense, because if all the, say in this particular case of 1/3, all the electrons are in the lowest Landau level, they all share the same kinetic energy, and then there's a big gap to the next kinetic energy level, that's the next Landau level, you can basically, and this is an oversimplification, but ignore kinetic energy. They all have the same energy. It's like they all have the same zero of energy, and there's a huge gap to the next kinetic energy level. So the only thing that really remains in the picture I'm showing you now is the mutual electron-electron interaction, and that determines all the physics. Of course, it's disorder. The kinetic energy cannot really be ignored, as I'm saying, but you sort of get the point that in this configuration, the electron-electron interaction will dominate the physics. And so if we do that, we learned, again, almost essentially 40 years ago, first there was the experimental discovery of the phenomenology of the fractional Coulomb Hall effect, but some very bright theorists told us, Bob Laughlin in particular, that under certain circumstances of filling, you can write down wave functions that have very important properties. One is they minimize the overall Coulomb interaction for certain models of the Coulomb interaction. So they actually lower that energy term and having a specific configuration of the electrons, and give rise to a gap in the spectrum, meaning that the ground state is separated from what we're going to call the quasiparticles or emergent quasiparticle states from the ground state. And if you have that configuration where you have a ground state that is essentially topologically protected, you have edge modes, and you have a gap in the bulk spectrum, you will see the phenomenology that looks very similar to the integer Coulomb Hall effect, although its origins are completely different. Okay, so what we get in the end is an incompressible fractional Coulomb Hall effect. All I mean by that is it has a gap and it shows similar phenomenology, even though in our single particle picture, we wouldn't have expected this at all. Okay, so let me go to data and then explain a little bit more about what is a consequence of
Can I ask a question?
Sure.
Can you go back to the previous slide?
Oops, sorry. Yep.
So in this electron interaction consideration. From the classical picture, then I would expect the Coulomb repulsion will just lead to a Wigner crystal.
Yes,
right?
and yes, that's absolutely correct. And I was skimming over those types of things, but yes, eventually you would expect exactly what you said, and that was
This is not a Wigner crystal, right? The Laughlin state.
These are the Laughlin states, or the, I've actually written down I think a Jane wave function, but I'm trying to skim over this, but yes, that's absolutely right. And that the Laughlin's insight, or from his trial wave function, is that this is actually a lower energy configuration. And what you said about there being the classical description leading to a Wigner crystal is absolutely correct. And there are, even in this quantum regime, there are particular fillings in which that is the lowest, the Wigner crystal or crystalline state is the lowest energy configuration, and you will get that as well. So, but at specific filling, at certain values of filling, this is the lowest energy configuration.
The Wigner crystal state will not give you the fractional quantum Hall effect. Is that correct?
Yeah, that's correct. Yes.
Okay.
It won't. Yeah. Again, I'm gonna have to make sure I don't say anything misspeak, but yeah, it certainly gives you a different ground state configuration, excitation spectrum, and all of that. And so it's different. And again, it depends exactly what filling you're at, which configuration is favored, and there's been lots of theoretical and experimental studies of this as well. Okay, very good question, and it's right on point that there are other possible ground state configurations. It's absolutely true. Okay, so the fractional quantum Hall effect looks very much like the integer quantum Hall effect, at least if you're a simple experimentalist like myself and you measure things. So here's a measurement made in a nothing special gallium arsenide quantum well, like I described to you earlier. This isn't particularly fancy or anything like that. It's just a representative. And so at relatively low magnetic fields, say 5 Tesla and below, you see the integer states, where I point out where we have integer filling, nu equals 1, nu equals 2, nu equals 3, nu equals 4. And there you see exactly what I described to you earlier, that the longitudinal resistance along the length of the sample is 0. It, in some way, looks like current is flowing without resistance. And while simultaneously or concurrently, the Hall resistance is quantized at a plateau value of h over e squared, 1, 2, or 3. Okay. Then I keep cranking up the field, and I start to see the same phenomena, meaning quantized Hall plateau and 0 resistance state, but it's occurring at rational fractions of the filling factor. And the most prominent one, is the reason I showed you this particular data in particular, is because at relatively small field, we can get to the 1/3 state at about 12 Tesla. And there's a host of other states, and if I showed you other fancier samples, we'd see many, many more. But the point is that the phenomenology looks quite similar, even though the underlying origins are quite different. And what was immediately recognized by the theorists is that the excitations of the fractional quantum Hall effect are emerging quasiparticles. And what do I mean by that? Well, first, the quasiparticles, and Laughlin recognized this, carry fractional charge. For the nu equals 1/3 state that I'll talk about, the effective charge is actually E over 3. Now, E is the fundamental charge of the electron. So it's a very funny thing I'm saying, right? We start out with a system of electrons. We build in these correlations driven by the strong electron-electron interactions, yet the excitations of this particular system carry 1/3 of the full electron charges. Somehow we sort of, broke the thing up, and we have less charge than we started with the original electron. And the point is that what's important here is this is a well-defined quantum number. It really is E over 3, and so that is one of the very unusual properties and interesting properties of the quantum Hall effect. Now, shortly thereafter, about a year or so after, it was recognized that one of the implications of this, or one of the possible implications, is that the braiding statistics or the statistics, the exchange statistics, are interesting and non-trivial as well, and that the fractional quantum Hall states should generate what are called anionic braiding statistics. And for the primary Laughlin functions, the 1 over m states, this can be viewed as simply as a Berry phase that's accumulated. So I have this little cartoon below. But the general prediction is that the anionic phase, and I'll show you what that means in practice or in experiment a little bit later, will be quantized in units of 2 pi e star over e. So what do I mean? These little vortices, these cartoon vortices represent the quasiparticles. So if I take one of the quasiparticles and wrap it around each other, what actually is supposed to happen is that the effective wave function describing the multi-quasiparticle system will acquire a phase, or the phase will change by a factor of 2 pi e star over e. So of course at nu equals 1/3, this would imply that the anionic phase that's developed in this, what we essentially call a braid, is 2 pi over 3. And this is first recognized by Bert Pelprin in '84, but shortly thereafter, Avro, Schrieffer, and Wilczek approached it from a different perspective in the way I'm describing it right now. And many people contributed to this development over the years, theoretically. Steve Gittleson, John Regime, there's been lots of people. But again, the point here is that these, it depends on how you look at it, but you say direct implications of having a fractional quantum Hall state, at least theoretically, of fractional charge and anionic braiding statistics, we're talking about 40 years later and just experimental demonstration. So it means that while they may be implicit in the underlying theory, their observation isn't so easy. Now for the fractional charge, that's happened quite some time ago. It happened in 1997 by a group in France and also Modi Heiblum's group at the Weizmann Institute in some very beautiful shot noise experiments. But again, that took until 1997 to demonstrate the fractional charge. Measuring the fractional statistics is even more of a hairy problem. And so I'm telling you about it in 2021, a very long time after it was the initial prediction. And I'm going to try to tell you why now. And I think from my perspective, it's an interesting story. So as I said, we're interested in measuring phases and the phases that develop when you braid one quasiparticle around another. And a natural way to explore this is to look at interference experiments. And what we're using is the electronic analog of the Fabry-Perot interferometer that you may have heard about from optics, but we're going to try to operate it both using electrons or quasiparticles and also do it in a quantum Hall regime. So if you look at this cartoon on the left, the blue region represents where the 2D electron gas resides, the sort of golden S and D contacts. So that's the source and drain. That's where we put the current in and where we take the current out. The magnetic field is applied perpendicular to this plane. And those yellow rectangles and objects you see on the surface represent surface gates. And they're used to define the electronic interference path. I apply voltages to those. I deplete the electrons immediately underneath the gates. And it also does another thing that you see a couple of these gates at the edges of the sample come in close proximity. And that's important. These are called quantum point contacts. And if you want to think of the optical analog, they act as beam splitters. But what they really do is bring these quantum Hall edge states into close proximity. And as I said, there's no backscattering in bulk samples because the electrons or quasiparticles, whatever state you're in, would have to scatter completely across the sample, across this big insulating state, and that the probability for that is very low. But if I bring the edge states in close proximity, I can enhance the probability for backscattering, and that's exactly what we use these QPCs for. So let's look at the path. So my edge state propagates out of the source contact and it comes to this first QPC. Now, most of the current continues on because of the way I've tuned the system into the interior of the interferometer, but some fraction of the current actually gets scattered across this narrow constriction joins the edge state that's going in the opposite direction and gets carried back to the source contact. As I said, because of the way we designed it and tuned it, most of the current actually propagates along the interior of the interferometer. I've defined that whole path by applying negative voltage to these gates so that the edge of the system is defined by this set of electronic gates. And that propagates on until I come to this second beam splitter, or QPC, at the far end of the interferometer. And again, because of the way we've tuned it, there's a finite probability for some of the excitations in this edge mode to propagate, or excuse me, scatter across and join the path that circulates around the interior of the interferometer and then rejoin the current that was scattered at the first QPC. Now, of course, most of the current propagates on into the drain contact. So if I were to look at what current actually propagates through the system, you can imagine that the backscattered current would be proportional to a couple of factors. Of course, there's basically the reflection coefficient squared at the first QPC. Okay, that's gonna obviously determine the backscattered current. There's the reflection coefficient at the second QPC squared. That will determine the probability for backscattering. But there's also going to be what I would call a cross term that goes as cosine theta. And what that is really representing is that if my device is such that the transport is coherent, meaning there's phase coherence along this entire interior path of the device, then the phase that's developed by this current that propagates along the interior of the interferometer, when it matches up with the current that's coming from the first, scattering from the first QPC, the relative phase of those two will matter in terms of how they add constructively or destructively. And so this phase I'm talking right now, this cosine theta, the theta here is what we call the interference phase. It's not itself the anionic phase that's an inherent property of the fractional quantum Hall state. It's the overall phase that's developed by this circulating current going around my interferometer. And the first term, say we're dealing with normal electrons in the integer quantum Hall regime, nothing fancy is going on. It's very simple. It's 2 pi AB over phi naught. This is called the Aronoff-Bohm phase. A is the area that's encircled by the interfering path, and B is the applied magnetic field. And that contribution is periodic in phi naught, basically the magnetic flux quantum, H over E. So you would expect oscillations to occur every time in the backscattered current, every time I go through a multiple of phi naught. Okay, so now assume I'm dealing with boring, uninteresting electrons. I'm in the integer quantum Hall regime, and I'm trying to measure the interference phase. Well, I can measure this interference by measuring the electrical conductance across the device. That's what the formula I showed you above for the backscattered current implies. And I can operate, as an experimentalist, I can operate this device in 2 ways. I can change the area by changing the applied gate voltage to these side probes, the little T's that you see that define the path of the interferometer. That's a gate voltage that I tune by hand. Or I can adjust the magnetic field. Basically, I crank up the magnetic field or reduce it to change the flux through the interior of the interferometer. And if you do this and you follow some basic calculations, you would expect lines of constant phase to have negative slope in the BVG plane. So what our theorist colleagues tell us is if we have the simple picture, and this is how the system behaves, I should see something that's been colloquially deemed a pajama plot in the community. These lines of constant phase having negative slope, and in the x-axis is the change in flux regulated by the change in magnetic field, while the vertical axis is changing the, again, in the simple picture, the area by tuning the gate voltage. And so this is the pattern I should see. And this was worked out in great detail by Halpern and collaborators, but it's also building on work that came before it from Shimon and Kivelson and Sandi and Wen, and also lots of theorists have contributed to this. And hopefully I don't slight anyone by leaving them out. But this is the expectation. Okay, now if I move to the fractional regime, things actually get a bit more interesting. Now this, again, I'm looking at the total interference phase, not just the AB component, but even the AB component becomes modified by or scaled by the effective charge of the quasiparticles that are circulating around the edge. So rather than being periodic and phi naught, it's, say in the case of nu equals 1/3, where you have the effective charge of E/3, the periodicity should reveal itself as 3 phi naught. So even AB contribution is modified in this significant way. Moreover, the anionic phase, the thing I'm really interested in, has a direct consequence. It should show up in this measured phase. The measured interference phase is proportional to the number of localized quasiparticles in the interior of the interferometer times this specific anionic phase that is a signature of the quantum Hall state that you're actually in. So again, in my cartoon fashion, I've shown this as this little spiral vortex that's localized within the interferometer. And as my quasiparticles circulate around the edge, the phase that's built up, the interference phase, will be sensitive to the number and specific anionic phase of those quasiparticles. So as you can imagine, if I change the system so that the number of localized quasiparticles changes, I should see discrete jumps in my measured interference phase. Why? Because the number of localized quasiparticles is a discrete number. It's 1, 2, 3, 4, but it's not 4.5. So that's not a continuous process. The number of quasiparticles changes. I'm again, making sweeping statements right now, but generally in discretely. And so you should see phase jumps or slips that come out and give you the measurement of this anionic contribution. Okay, so what's the problem and why am I talking about this 40 years later? And what's going on? What's the big deal? Everything I said to you is pretty simple. So the expectation is this Aronoff-Bohm interference pattern with a periodicity of phi naught and lines of constant phase with negative slope. But even in the integer regime, this isn't what's seen in experiments. And so leaving the fractional Hall effect aside for the moment, let me show you an example of what's typically seen. So in reality, if you measure such a system, a small interferometer, which you want to be small because you want to be coherent, you do measure lines of constant phase in the B delta VG plane, but they have the wrong slope. And this is what's a direct consequence of the strong bulk edge interaction that I've completely neglected to this point. We call these Coulomb dominated oscillations. And so what's really going on here is that the edge, the compressible edge state that's at the periphery of the sample, if I need to change the charge in the middle of the interferometer, well, that has consequences. There's electrostatic energy associated with that. And the system will change itself to minimize that energy. So because of strong bulk edge interactions, this actually causes the area to change with magnetic field. I've considered so far sort of an inert object. The area of the device doesn't, is only changed by my gate voltage. It doesn't randomly change on its own. But what is really true, because you have to take into account the strong bulk edge coupling, that you can't change A and B independently if you're in this regime of strong coupling. The flux actually, it turns out, decreases when I increase B. That's very strange. I tried to increase B, yet the net flux that's through the interferometer goes down. And so if you do the analysis like Halperin and collaborators did, you find out that you actually do expect a pajama plot that has these lines of constant phase with positive slope. Why we care about that is, in principle, it makes braiding unobservable. And if you're in a strong coupling regime, the change in area that comes about because of this Coulombic effect between the interior charges and the charges at the edge completely cancels out the anionic contribution, again, in a certain limit. And you'll never see the effects of adding or removing quasiparticles, as I described to you before. So this, if you're interested in anionic phase measurements, this is a real problem. And so we have to somehow overcome this. And this has been a major challenge. So I'm not going to spend too much time on this as a detail, but what type of behavior you get really depends on the ratio of a few microscopic parameters. And you can go all the way from the pure, what I call the AB regime, where you have lines of constant phase with negative slope, to intermediate coupling regimes where you get sort of checkerboard patterns, all the way to this Coulomb dominated regime where you have lines of constant slope with, lines of constant phase with positive slope. And it all depends on the ratio of some couplings that I don't want to get into in too much detail in this talk, but basically it KIL parameterizes this bulk edge interaction, and KI, which basically you can think of as the energy cost to add charge to the edge stiffness, if you will. The critical point for our discussion is that theta anion is unobservable in the, what I call Coulomb dominated regime, because the phase change is just a multiple of 2 pi. And obviously you can't see any phase changes of 2 pi. Okay, so how do we fix this? Or how is this recognized? Well, there's some early experiments by my friend and collaborator, Charlie Marcus, that really pointed us in the right direction. So back in 2009, Charlie did what I think was a really crucial experiment. He made 2 types of interferometers. A small one, which by small, I mean 2 micron square area, that's the one on the top, and a big one, which is 18 micron squared, the lower one. Now, both of these had surface gates on top, these big surface gates that cover the entire interferometer, and one of the purposes is to try to screen some of this bulk edge interaction. Okay, so what did he see? In a small device, he saw what everyone else saw. This Coulomb dominated behavior with lines of constant phase having positive slope. Now, the oscillations were clear and you could see them because the device was small, but it's certainly not in the right regime for the types of things we want, the physics we want to expose. Now, he made a big device as well, a huge device. Now, what does this do? This is going to reduce the bulk edge by making it big, the bulk edge coupling. You can think of it in terms of capacitance, right? The self-capacitance of the device. I dramatically alter the self-capacitance by scaling the size of the thing. And if you want to, for the experts, think of a charging energy of a quantum dot, I greatly change the charging energy of this system. And so it was really nice in this, he saw AB, again, what I call AB type oscillations, where we have lines of constant phase with negative slope. But I do want to point out the field scale at which he saw these. So if you look down at the x-axis of the bottom plot, it's about 0.5 Tesla. And the problem is this is way, way, way deep in the integer regime. It's nu equals 20. And the problem is that the oscillations fade as you increase the magnetic field. The device becomes less and less coherent and everything gets washed out, so you can't see anything. So that's just a consequence of he has this huge area, huge perimeter, and you have to maintain phase coherence around this big object, which becomes progressively harder and harder. So it was a key insight is that you can alter the bulk edge coupling. One way is changing the charging energy of the device, but just making it bigger is not going to work because of the poor coherence. And so if anything, our key insight or innovation is just the following. Well, Charlie has built a capacitor with a surface gate that's relatively far away from the 2D layer where he's trying to screen interactions. And we know that we can, if we change the distance between the capacitor plate electrodes, we change the capacitance and we can modify this screening ability greatly. We have at our disposal this MBE machine that allows us great flexibility. So why don't we just grow in situ a fancy capacitor in the semiconductor structure itself? This has 2 advantages. One is that we can put the layers in real close proximity to the primary layer that we want to probe and experiment. And we can control the densities of these metallic sheets that are nearby. And that gives us advantage as well. So, this is really the crux of the matter. And so I do want to spend a little time on it because it's really what allows everything that I'm going to tell you afterwards to fall out. So in the center region, we have this primary quantum well. That's the blue region that says 30 nanometers of gallium arsenide. But in close proximity, essentially 25 nanometers away on either side, we grow in two additional two-dimensional electron gases. And if you look at the conduction band profile and the density, electron density in the simulation I show you in the middle, what you see is something interesting. We have this sort of low, relatively low density electron gas in the middle, and then really close by, we have these high density, right? You can think of as metallic sheets that we can use to screen the strong bulk edge coupling in this type of sample. Now, you could also say, wow, what a pain in the butt. You want to look at 2D properties, and now you've just made this triple layer of 3 quantum wells in really close proximity. How are you going to look at, and the one you want to look at is low density compared to the other ones that are in close proximity. So how are you ever going to pull out the transport that you're interested in? Well, this makes our device fabrication more complicated, but there is a solution to that. And that's sort of, again, shown in the cartoon fashion on the right. We will have our tiny interferometer in the center of a mesa. That's all these yellow gates coming in to this little tiny object you can't even see. But we will use other gates to selectively cut off the conduction path through these screening wells so they don't obscure the physics that we're interested in. Now, that does not mean we've cut off the screening wells from doing their job in screening. They're still fully populated in the local vicinity of the interferometer. They just don't show up in transport. And so this is really what allows everything to happen. And we had this innovation in design, but then we also borrowed heavily from a fabrication technique that was developed by Jim Eisenstein back at Bell Labs to explore highly correlated bilayer systems. He was interested in very different physics, but he wanted to selectively probe transport through one layer and not the other, and then measure the other or measure them in parallel. And so I'm going to cut through all the details, but basically we still have all these 3 wells in parallel. Our ohmic contact, where the current flows in, flows out. Of course, we can't separate out. We contact them all simultaneously, so they are in parallel. But then we use gates to selectively depopulate the screening well in the vicinity of the contact. And the top one, we apply a relatively small voltage to the top. That will deplete the top screening well. We've done some things to make the whole structure very thin. And then we apply a voltage on the back that cuts off the lower screening well. And then even though the contact itself, the nickel, gold, germanium ohmic contact that you see is shorted, transport can only happen through the primary quantum well that I'm interested in. And again, this was a technique that was developed for another purpose by Jim Eisenstein, and we just wholesale borrowed it. But that was good. Okay, and the point is our little interferometer, our tiny little object, is still way, way far away in the center and isolated from all this behavior. So the screening wells are still there and will screen the strong bulk edge action. What does this allow us to do? It allows us to make a really small interferometer. Why is that good? Because of the coherence factor. We want to keep it highly coherent. Smaller is better. But normally we would have been crushed by this strong bulk edge interaction. But because we have these screening wells, that is strongly damped in this particular configuration. So it allows us to go to a really tiny device, improve coherence, but also maintain low bulk edge coupling. There's other reasons why it's good too. I don't have to go into this, but since it's listed here anyway, simulations indicate that it promotes a steep confining potential that limits edge state reconstruction and all sorts of things that happen in the fractional quantum regime that you don't necessarily like, but are a consequence of the confining potential. And we sort of worked some of this out in simulation back in 2018, and it guided our development of the devices. So I know I'm already running over, but I'll try to get, the point of all this was to tell you how we got to the point of measuring anionic statistics, and hopefully everyone will appreciate at least how the device is designed and what's going on. So imagine, again, this is a little bit for the experts, but the charging energy, which serves as a proxy for measuring this bulk edge coupling. If we didn't have, and we made a device that's really small, just like the one we're measuring, but we did it without screening wells, and we went into a different regime at B = 0 and measure something called Coulomb Blockade. That is something that allows us to measure the charging energy and basically characterize the capacitance of the system. And for the experts, these are classic differential conduction measurements and that allow us to extract the charging energy. And these black diamonds that you see are the forbidden area where we can't put electrons on and off because it costs too much energy. And that allows us to characterize the charging energy, which is about 200 micro eV. This really looks like a quantum dot because it's really small. Now we make the same small device, but only on our screening well samples, and we have all these gates all around the thing. And the charging energy is reduced by an order of magnitude. If we tried to build the Coulomb diamonds, we see that the charging energy is really, really small. And so this is an experimental confirmation that the screening wells are really working. Okay, so again, I'm running behind, so let me get right to the chase. Now we first take our interferometer, we take it away from B equals 0, we open up the QPCs so that they're nearly fully transmitting, not pinched off in the Coulomb Blockade regime, and try to operate as an interferometer at nu equals 1. And here, what you see is classic Aronoff-Bohm behavior that is indicative of weak bulk edge coupling. You see negative slope to the lines of constant phase, the Coulomb charging energy has been suppressed, and what's really neat is that we're able to do this in a device that's 20 times smaller than possible with just surface metal gates. And what's really neat for someone like me trying to measure things is that the interference is large, amplitude, and robust. In the integer regime, it survives up to hundreds of millikelvin. And if you look at the scale, for the color scale, we're measuring changes of kiloohms. And this is, anybody can measure this. This is really easy. So it's really neat. And so we just have a robust device in which we see what we expect in the integer regime, and it's pretty impervious through the thermal smearing and all sorts of things. And so that gave us good confidence to move into the fractional regime. And now I'm showing you our initial report that happened in 2009, and what I believe is the first observation of Aronoff-Bohm interference in the fractional quantum Hall regime. And again, you see these lines of constant phase having negative slope. The slope and periodicity, though, is changed, and that's an indication of the fractional charge. We can scale these field periods and gate voltage periods and extract the effective charge, and it comes out really close to E over 3. So it's a measure of fractional charge, but in some ways this result is a little disappointing because now we have AB oscillations. We built a device, and you say, okay, shouldn't you see these anionic phase contributions? And we don't in this particular experiment. We see the fractional charge, but as I told you, that was already measured and known from 1997. So I'm not adding much to the field by claiming that what the charge is. Nevertheless, it does show that the device works and the architecture works in principle. And this was our first report back in 2019. But you say, okay, what's going wrong, or why don't you see the anionic phase? And in hindsight, and again, the theorists gave us key insights, we know why. And if you look at the field scale at the bottom of this plot, we're at 13 Tesla, but we don't vary the field very much, and that meaning we don't explore a wide range of magnetic field. And the reason being is because at very high fields and at this density of electrons, the device isn't super stable. You can't go over a wide range. And the reason for you have to go over a wide range is now known because of work by Rosenauer and Stern. And this was in the theory paper from 2020, actually after a conversation I had with Adi, Stern, and Byrne. And what's really going on here is that there's a competition between the energy costs. Now I'm getting a little bit into the weeds, but it's important. Competition in energy costs between creating a quasi-particle, which will manifest itself as a phase slip, and the electrostatic energy cost to keep nu equals fixed. And what we've overcooked it in a way. We've made the charging energy so small that it's actually energetically favorable for the system to maintain constant filling, not creating quasi-particles, just change the charge density, if you will, to keep filling factor exactly at nu equals 1/3, okay? And that will exist over some range of magnetic fields. Say we start out at B equals 0, and this is just a cartoon again, and we start varying the magnetic field, and we'll see exactly what we saw in our 2019 experiment. We see this change in periodicity, but all we see, or the scaling of the periodicity, but all we see is the AB contribution because we haven't actually introduced any quasi-particles. Now that only goes on for so long, so we see a 3 phi naught periodicity. Eventually the energy costs for adding charge become sufficient, that the lowest energy configuration is actually to add quasiparticles, and then we should see a jump, a change in phase, and manifestation of the anionic phase. And so just in cartoon, if you want, the chemical potential is fixed in the middle of the gap. There's no quasiparticles, so all we see is the AB contribution, and you have to get far out in magnetic field in order to see the contribution of the quasiparticles, except for in isolated cases. And oops, that's a mistake. Sorry, that's backwards, but it just shows that it should happen on both sides. So let me move on. Anyway, I don't want to get down too much in the details, but there was a calculation done of what we should expect for this field range, and the measurement from 2019 was completely within the range where we expect no quasiparticles. So this tells us exactly what to do as experimentalists. We do two things. We make the device smaller, we increase the charging energy, and we also make the density lower so that we can actually, that's a technical thing, but that we can probe over a broader range of magnetic field within the stable device configuration. But basically, we substantially reduced the size and we went to lower density. Okay, so the upshot is we can examine interference over a broad range of magnetic field of 1/3. And here's what we see, much broader range, and we have the same AB oscillations that you see with a negative slope and the 3-5 periodicity, but now you see some glitches in the data and you say, oh, that's just junk in your data, but it's really not, because if you actually look at these these glitches or phase flips, it turns out they are well matched to the anionic phase contribution we expect at 1/3. So as I said much in an earlier slide, the interference angle or phase will have both the AB contribution scaled by the effective charge plus this anionic contribution. Okay, so when the quasi-particle number changes, you should see phase slips that are integral multiples of the anionic phase. So what you do is you fit the conductance between the jumps to the following form to get the phase jumps. And if you actually do this and then calculate what the phase jumps are, they are all centered, well, delta theta over 2 pi comes out very close to 1/3. And so if you take the average, the delta theta, it's minus 2 pi, 0.31 plus experimentally 0.31 plus or minus 0.04. Yeah, 0.04. And of course, theory tells us it should be 2 pi over 3. And as an experimentalist, this is my feel is this is pretty darn close. And so this was very good in that I want to show you that it's actually reproducible. This isn't noise in the data. We can do this time and time again and change the conditions and repeat the scans and get essentially the same answer with each one of these glitches. And so they're at the same magnetic field gate voltage values. You get the same value more or less for experimentally at each one. So it's just not random noise. And all these observations are consistent with anionic braiding and the anionic phase of 2 pi over 3. So I need to wrap up. I know I'm running late. There's lots of other things that I could describe to you, and maybe I should skip through these, but I want to show you something interesting about some new experiments that we're doing. And again, what the theorists told us is we should see a really clear transition between this, the discrete phase slips associated with introducing through random disorder quasiparticles in the central region and transition to phi naught periodicity. So basically we should go from 3 phi naught to phi naught as we expand the magnetic field range. And in another device, we see just this. The central region has the 3 phi naught periodicity. We see a discrete transition to phi naught periodicity as expected. We see really clear phase slips. Now this is all at 10 millikelvin. If we increase the temperature to 90 millikelvin, this is a smaller device, I haven't gone into details, things get washed out, but it looks more like our original data. And so that's consistent as well. What I really want to zoom in on, and for the experts, here's a plot that really focuses in on the transition region and the sharpness of the phase slips. So if you're saying this is junk, in this regime, say at 7.5 Tesla, you see these phase slips associated with introduction of individual quasiparticles, which, clear phase slip, just discrete. And then as the magnetic field gets larger and larger, you see a transition to a different periodicity from 3 phi naught to phi naught. And this is allowing a great deal of new experiments to go on that, as far as we can tell now we can always be wrong. Everything seems consistent with this interpretation that we're measuring anionic phase and extracting it in a clear and reproducible way. So I'll jump to the conclusions. The whole key for what we did is relatively simple. We had to just suppress this bulk edge coupling that's been plaguing the field for quite some time. We did it with screening whales in the heterostructures. We had that capability because the MBE machine is under my control, and we designed that. Then everything else follows. The measurement of the Aronoff-Bohm interference in the fractional Coulomb Hall regime was the first example of this, and then this direct observation of anyonic braiding statistics that seems to be well matched to theory was the second consequence of it. And I think this gives us a really nice, looking forward, a playground for how to expose these types of effects and move on to potentially even more intriguing fractional states. We started with 1/3 because it's the strongest state. It's the most well understood. Theoretically, it has the ease or the simplest edge structure in the fractional Coulomb Hall regime that you could hope for. It was easy. Now let's see if it can tell us stuff about more complicated states, and that will be really fun. So thank you for your attention. I know I ran over, but hopefully some of the background and why we're doing this and how we got here is now clear. So thank you for your attention. I appreciate it. And I welcome it. I know it's late, but if you have any questions, please ask. Anything that wasn't clear, please ask. Thank you.
So let us thank Professor Manfra for this great talk. So any questions?
Hi, Mike. Can I ask a quick question?
Sure.
It's Andre.
Yeah.
So I'm curious, what's the lesson for future maybe experimentalists? In order to achieve success in quantum Hall, one should grow their own samples, should not rely on third party.
I didn't say that, and honestly, it's really hard because you have to try to be expert in a couple of things, and that doesn't work so well usually, and it doesn't work for me particularly well. This was a lucky combination of circumstances. If you're working close, so people who focus on growth and that's their thing, that is a full-time job. And if you're working closely in what you might call a transport experimentalist working very closely with a grower, you could have done exactly the same thing. Mm-hmm. All I'm saying, it's not impossible by any means. All I'm saying is I've been doing transport for many years anyway, and I have a transport laboratory, and just the ability to quickly build these samples and go through them and all of that facilitated progress. That's all I'm saying. But there's many. Let's look at the prime examples in the heyday of Bell Labs, the growers and the measurers, if you will. I don't make the distinction because I don't make the distinction myself, but if you want to, we're right down the hall from each other, right? You look at the Weizmann Institute. They have great capabilities in both. It's certainly useful to have all these people in the same area and talking to each other and spitballing ideas and all of that. That is an advantage. I don't say you have to do both.
Well, by you, I meant the group. It doesn't necessarily mean a single individual.
I still, it's, I don't know.
But maybe
I look at my life right now, and I don't know. I don't think I would wish this on anyone. So, I think there's really great experts in both areas, and
I'm just somebody who joined all of this much later due to my age. I'm trying to understand what's the main step that led to the progress, because there was very little progress for the amount of time that I cannot really imagine. 40 years is longer than my life.
Yeah, well,
so what's the main?
It's not that far from. I think I was 9 or 10 when this all started too. I'm a little older. Well, you have to learn too, right? I mean, there's a lot of learning that goes on by these other experiments. Like I said, the learning from, Charlie's experiments, it wasn't obvious to me or anybody that was the issue. And, Bob Wills done a lot of experiments, and the Weizmann Institute has done a lot of experiments. And it was for us, it was just looking at what wasn't working and what gave a hint of what could be working. And we just sort of built on the learnings of others. Then we had the ability to execute, right? We can make samples, and as I said, we have a transport lab and all of that, and fabrication facilities. We could just, so it's not as simple as just saying, oh, yeah, the same group has to do all the things and then it'll all happen, right? It's not like I invented this field or anything like that. I learned a great deal along the way from others, and others, what you might call failures. Failures are great, right? Because they teach you about what the problems are and what the challenges you have to address are. So, there's no bad data or anything here. It's just how you learn, and then you try to leverage that to your ability. As I said, I also leveraged something that was developed by Jim Eisenstein for another purpose. And so it's complicated, right? It's not, and I don't want to take any too much credit or anything like that. It just happened in my lab, that's all.
Thank you for the explanation. Thank you for good talk.
Yeah. Thank you.
And so maybe I can add one brief comment that there are actually very many interactions that are relevant here, including interaction with theory, because a naive theory that dominated that field for most of the 4 decades was telling that one doesn't really need to produce something very complicated, like the samples that we just saw. That's actually pretty trivial, at least in the integer Hall effect. So when people began performing integer quantum Hall experiments and saw something exactly opposite to what theory predicted, that was at first a major puzzle. And it took much time till theoretically it was all sorted out, because as it turns out, it's extremely non-trivial on the theory side what's going on.
Yeah, and I hope I didn't give the impression I'm an experimental, but that is absolutely true. And it isn't so easy to sort out, and I didn't delve into the details of the theory, but it is complicated. And balancing all these different energy scales and all of that, and sorting it out in by many theorists. I've cited a few, but there's many people who've contributed, including Dima and others, Andre. Took some time. It's pretty messy in reality, and we are certainly were guided by that. And as I tried to point out, and maybe it wasn't clear enough, we were sort of a little bit at a loss why we weren't seeing we got into the regime where we had weak bulk edge interactions in our first paper, but we saw the fractional charge, but we didn't see the anyonic statistics. And, again, I was complaining, I think it was to Bernd and Adi, or it was probably at a March meeting or something. And lo and behold, all of a sudden this paper shows up on the archive, and then they sent it to me. But I'm saying, that's it. So really, in the second set of experiments, it's like, okay, it's clear what to do. Let's make the device smaller and lower the density, and so we can operate in this broader regime and have greater control. And voila, things popped out. And so, there's also the guidance provided by theory, which tells us about what we may or may not potentially see, but the details of how to get there theoretically are not obvious, as Dima is pointing out. So that is a huge contribution as well.
So can I ask you another question? So you mentioned that you are pursuing other filling factors. So could you tell what filling factors are the most immediate target?
Well, immediately, I mean, of course, the holy grail is 5 halves, but getting there is now, as an experimentalist, that's a real challenge. But the first thing we want to do is to go to non-Laughlin states and even more primitive states that have potentially complicated edge structure. 2/3 and 2/5 are the ones that are in the neighborhood that we're going to immediately play with, right? We can go to hierarchical states, and also where 2/3 where you can have many edge reconstructions and give rise to all sorts of complicated behavior, and it's not really understood experimentally, is my feeling. And you can also, something that's interesting to me is I think you may be able to do more complicated experiments I haven't talked about, differential conductance measurements and looking at the behavior of the current in these different states, extract something, perhaps say something meaningful about how well the edge states, and again, this is down in the weeds, but described by Luttinger theory, right? How well do these Luttinger, approximated by Luttinger liquids, these edge states, and there, if you go down into some of the theoretical predictions, it would say that you can use this as a probe of that type of behavior, and that's also something that I find very interesting, and we're doing right now, is to see, can we say something interesting about the edge structure in any particular configuration?
So any other questions? So it looks like we are way over the time.
I know,
some persistent people are still here. So I just want to make sure that maybe someone was staying here for such a long time to ask a question. So if
no one has a question, I'll just ask, because I mean, if Mike was willing to answer.
Sure, I'm willing to answer. Again, I apologize for running over. I'm trying to get all the introductory material in and then get to the point, and I don't do a great job of it, but.
I mean, that's great. That's why online seminars are good, because whoever didn't want to stay left, and we can talk.
Yeah, great.
Can you say maybe a couple of words? What's difficult? Again, I'm much less of an expert in this even than Dima, and Dima is a theorist and you're experimentalist. What's the fundamental obstacle, fundamental difference for going to 5 halves? Like, what is it? It's still gallium arsenide, but I assume there's something
There's
that's
lots of things. So let's leave experimental challenges aside for the moment, and just talk about the difference of physics, right? This is, first of all, a much more fragile state in that, the gap is fairly small, even in the best samples. I mean, we've measured at least in bulk measurements, we've measured some of the largest gaps at 5 halves in a completely different sample design, and it's still only on the order of whatever, 650 millikelvin or something like that, right? Where the gap at 1/3 is 6 or 7 Kelvin, is huge. Secondly, the edge structure is really, in principle, I mean, they're not even worrying about softness of the confining potential and reconstructions, in principle, is much more complicated. And if you're trying there's supposed to be neutral modes, and these can have important consequences, but one of the most straightforward ones is that you need to be backscattering and interfering an inner edge mode. So as you go up in filling, you'll have more and more edge modes, right? And they move closer and further away from the edge. And the confining potential changes dramatically. And it's really important. One of the things, that technical things I didn't get into, and I think is one of the things that distinguishes our experiment from others, is that the screening well design really promotes sharp confining potentials at the edge. Soft confining potentials are a real bugaboo, because there's the obvious one, they result in lower edge mode velocity. Basically, if you're in a regime where the confining potential is soft, then the edge state, whatever it is just moving slower, and therefore it impacts coherence. But it also allows for reconstructions, and I think that's a problem in a lot of experiments. And I don't know if you've been following the results out of the Weitzman group, but there's a lot of craziness that comes out, that not craziness in it's crazy, but just complicating experimental observations that may be due to the softness of the confining potential. And we in the screening wells often see very different behavior. And so it's, what's at the edge isn't just some thing that's set in stone by you're at a particular state. It also, there's many possible configurations that are allowed or potentially allowed depending on the specifics of the device. In any event, at 5 halves, you're necessarily scattering in inner mode, which is always more problematic. So and again, if you're still interested, I can keep talking. This being in, like, again, Dima has a different definition of what's Coulomb dominated and what's AB, but I'm just using a very hand-waving or experimentalist view. When I have the lines of constant phase with negative slope, I call that AB, and when I'm positive slope, I call that Coulomb dominated. It's not strictly correct, but that's what's we experimentalists use.
Well, we call your regime incompressible. And
no, I don't want to argue. It's perfectly fine.
IB and Aharonov-Bohm is only in the compressible regime. What you did, you reached a regime that was somehow lost by theorists. Very early work assumed incompressible samples. Then smart people realized that they're actually always compressible, and there was considerable experimental evidence. Then all theory focused on that. And then you managed to produce an incompressible sample with this very smart gating.
Yeah, and so again, it's not to argue about definitions. But what I mean is, you can switch. This is a central point. There's whether you're in a certain regime or not completely depends on how you've configured the device and how you're operating it. What I mean by that is, I can, in a the small device that I'm probing at 1/3 to tell you all about transitions between phi naught and 3 phi naught periodicity. If I go to filling factor 3, very boring, integer quantum Hall state, I can just an experiment, flip the directionality of the lines of constant phase. Okay, meaning that there's no one, you can't, it's specific to the physics and device or the regime you're trying to probe, and any particular device has to be tailored, and heterostructure by extension has to be tailored for that particular experiment. What I mean is, I can go to a regime where the bulk edge coupling effectively is stronger because I've changed these coupling constants, and at nu equals 3, I'm scattering in inner mode that's in a softer part of the potential. So, these ratios of KIL, again, this is getting down in the weeds, but KIL to KI, sorry, there's 3 of them. KIL to KI can change even within the same device at different fillings and different bias conditions. And so, extending what we've done at 1/3 to 5 halves, even as a matter of principle, is complicated, and as a matter of practice, it could be really, really hard because of, again, the fragility of the state, the complications of neutral modes, and all sorts of things. So,
so that's why 2/3 and 2/5 seem like the reasonable next steps, because you have to figure out how to deal with multiple modes.
Yeah, that's right. And I want to do that in a state that, in some ways, is not so, how to say this, controversial. Right? If I can convince you, so this is how I convince myself. It's not really probably it's not the only way by any means, or even the best way. I go to nu equals 1, nu equals 2, nu equals 3, where I say, okay, the underlying physics can't be that complicated, and does my device behave as expected, and can I control it? And I want to show people that, so when I make claims at 1/3 about its operation, even at 1/3, there's substantiating data that says, hey, they kind of know what they're doing and they have control of their experiment. A little bit of the issue is 5 halves is so wide open in terms of how you interpret the data that's a little bit of a problem if you don't have everything you can't be quantitative about other things that you should know very well. And that's my approach. So okay, we knocked off the easiest thing, or we're still working on it. Still, the stuff at 1/3 is interesting to me. But then we go to 2/5, and then we go to 2/3, and then, in parallel, we're trying to design structures that would work at 5/2, but that's going to be a big step.
So since you mentioned the filling factor of 3, so I wonder if you see any analog of pairing behavior that was seen by Heiblum and Ashuri in completely different experiments for filling factors between 2 and 5.
Yeah, we do. You mean in the halving of the periodicity?
Right, because that's another complication for interferometry at 5/2, it seems. Unless one understands why that pairing happens, it happens right at that filling factor too.
Yeah. And so we see in that regard, in terms of this pairing or experimentally as the halving of the periodicity, we do see exactly as Heiblum and Ashuri see. Meaning that does show up in our experiments. That wasn't exactly what I was talking about, but I think that's an experimental fact, and how to understand it exactly. And again, it becomes so complicated at 5/2 because you have, and there's multiple charged quasiparticles that are circulating around, right? So there's the E/2, there's E/4, and so
usual fermions too. They mess up with interference, and that's
yes, of course they can
get them out with Coulomb, with any sort of Coulomb interaction.
Right, and they can decohere the system, and it's just that's really hard. So the interpretation of data at 5/2, from my perspective, is that I want a device that, at least in the vicinity, I know really well at 2 and 3 and maybe 7/3, and that I can say, yeah, I fully understand what's going on here in a quantitative way, not just speculative. And then I apply it to 5/2, and then we can sort out the data. In the absence of that, it's really hard, in my opinion. But not everyone agrees with me, of course. But
and 8-thought and 7-thought are not entirely without controversy. I think before Ashuri's data that 7-thought doesn't seem fully polarized, at least all experiments seem to show in the same direction. But as you know, numerics is all over the map. So numerical people generally tell that 8-thought is not a simple Laughlin state. Something else, it just experimentally, it always seems to be a simple Laughlin state. So it's extreme mess, even there.
Yeah, it's a mess at 7/3, but it's not as bad as 5/2.
And at source, it's mess in the following sense. Experimentally, it all seems to be a boring analog of 2-thought states. But numerical people will tell, no. What we see is much more interesting. Just experimentally, no signs of that.
Yeah, but what I want to say is I go to 7/3. Well, I don't know what the answer will be because I haven't done it yet. But if it is boring, that's good for me.
Yes. Otherwise, how you calibrate?
Yeah, that's right. Exactly it. And if I go to 7/3 and it's boring and consistent with what we've seen in all the other experiments, that's good, because then the nearby fraction I can try to say something about, rather than just where we
So what is your plan about light? So when you work on the second Landau level, do you plan to shine light like Bob Willett does, or you would avoid that?
I also wanted to ask that. Do you need to illuminate?
Well, in all the experiments I'm doing right now, the answer is no. At 5/2, we are designing samples and device structures that we hope, and this is what I said in parallel we're doing, that may be amenable to shining the light and also be simultaneously stable for gating. Now, there are many ways to approach this, and you could do, I'm sure you've seen recent, and this is something that we've done in the past too, is you look at compromised device structures, like Modi just put out the most recent noise measurement paper where they had a heterostructure that looks like a doping well on the bottom, but looks more conventional on the top in terms of the doping. And they try to, get as much benefit from the doping well structure that gives rise to these large gaps at 5/2 and the beautiful spectra that we see, but also can still be gated with some stability. There are also, in our experience, and this is just an experimental fact, the best transport in the n=1 Landau level usually comes as a result of illumination. It doesn't change the mobility. It doesn't change, those other parameters that you would typically go by. But the quality between 2 and 3 can be dramatically changed under illumination, because it just, basically puts everything far out of equilibrium, and then when it settles down, there's presumably correlations between how the impurity, the donors are then configured and screened. And so it would be good if we had samples and a device design. That's what I'm saying. It's not just the samples, it's also the device design that allow us to illuminate if necessary. And that's one thing we're pursuing right now. But there's also trying the way that was reported in Modi's most recent paper as well. And that's something we're doing now.
My concern with illumination is that indeed you drive everything out of equilibrium. So at the most fragile filling factors, it's not at all clear if you don't change the ground state. This is extremely fragile, extremely disordered system, and the ground state is a compromise of multiple filling factors that are actually present in the bulk. Perhaps it will be less of a problem for a very small interferometer that will be roughly uniform. But for bigger samples, you have extremely non-uniform system. And when you shine light, you just may break the balance of different regions with slightly different filling factors. So it's not at all clear what's going to happen. That was always my concern about Bob Willis experiments. Is he even testing the same state he would have without illumination? I don't know.
The answer is, well, no. Yeah,
if the answer is
really
no,
complicated. It's really
matter.
Actually, it's really complicated in these structures, these interferometer structures that have multiple length scales in them. And
yes,
what state is being directly probed, and what region that exists.
Yes, that's another issue, because the area of his interferometers makes no sense whatsoever. That was always an issue with interpretation of his data. Big issues and everything else.
Yeah, this part isn't being recorded, is it?
Everything is recorded. Well, okay, I can stop it because I think it's.
We can always ask.
Okay, no, I think it's time for us to stop recording.
I think it's time for you to stop recording.
Okay, because I think the colloquium is well over. Let me stop recording indeed.
Oh, Dima, I'm just trying to tell you that you.